Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, nama saya Adelia Neyoan dengan NPM 23351089. Saya berasal dari kelas 6F. Di sini saya akan mempelajari bagaimana cara agar kita dapat berinteraksi dengan hardware dengan cara menonton video pembelajaran.
You ever wonder how your code really controls hardware? I know I did when I first started out. Back then, as a web developer, I would write a line of code, and like magic, something would appear on the screen. I kept wondering, how could something abstract as code control something as physical as the liquid crystals in my display? My colleagues at the time didn't seem to care, but I just couldn't let it go. Years later, I am now an embedded systems engineer, controlling hardware for a living. Meanwhile, those same colleagues are still centering it. Probably making twice as much as me, for reasons nobody can really explain. But I, at least, finally found out how code really controls hardware. It turns out there is one simple mechanism behind it all, and once you understand it, you can control anything. And in this video, I'm going to prove it by controlling these four devices: an LED, a trimmer, a printer, and yes, even a laptop. And I will show that all it takes is basically this line of code. But heads up, learning it doesn't come without its risks. The mechanism I'm talking about is called memory map IO. Sounds technical, but it just means your code talks with hardware with memory. From your code, memory is just a big range of addresses you can write to and read from, just rows of numbered boxes holding values. In a high-level language like Python or JavaScript, you may never come in contact with memory directly. But if you ever use pointers in C, that's all they are, a way to access one of those boxes directly. Most of the time, you're working with regular memory like RAM or flash, but some of those boxes are wired up to hardware instead. That's what we call memory mapped IO. On the surface, they look like regular memory too, but when you write to them, there is hardware on the other side that reacts. To make it more concrete, it may help to think of memory like a box with drawers. Most drawers contain safe, boring things like code or data, but other drawers are wired up to actual hardware like a giant thing. And there are also some drawers probably shouldn't touch at all, but we will get to that later. Before we get further into how this mechanism works behind the scenes, I think it's best if we first get the scene in action, starting with something simple and familiar, the Arduino, together with one of its basic sample programs, Twinkie. Use a tiny code sample that sets up a pin to an LED and toggles it every second, building and uploading it. The LED blinks, no surprise there. But what does this code really do? I mean, most code we come across reads like this. A couple of high-level functions that do what we want without us needing to worry about the details. It's a nice, convenient abstraction designed to match how our brains like to think, in language, not in numbers. But peek inside, past the helper functions and defines, and you will see that underneath, the code is really just interacting with memory. And we can do the same by simply replacing these functions with pure memory writes. One write to configure the pin as output, and then two writes to turn the pin on and off. You find these addresses and values in the microcontroller's datasheet. And this is the way we write a value to a particular address at C, a pointer to the address, and then dereference to set the value, and not forgetting the volatile keyword, because it essentially tells the compiler this memory is not like regular memory, but don't optimize it away. As you can see, understanding pointers is key to control hardware. By the way, if you ever miss me, despite my frequent video uploads, I also write the occasional practical note on embedded systems. You can sign up for that at artforvibes.com. Alright, back to the demo again. After swapping out those function calls with memory writes, if everything works as it should, the LED should blink as before, so it can upload again. The output gets smaller now, which is expected, because we're no longer using the code provided by the Arduino library, but instead interacting with the memory directive. And yes, the LED blinks as before, but I don't expect a single example to be enough to make anyone a true believer of memory mapped I/O. So let's go bigger. This time it's my old trimmer hooked up to another small computer, well, a microcontroller, an STM32 to be exact. It reads the input from the button on the trimmer and sends signals via the motor graphic chip to the motor inside that drives the trimmer head. STM32 is a good example because these chips are in everything these days, and if the code running on them also controls hardware or memory, we are onto something. For a setup like this, with an STM32 and some stuff, there will again be functions doing most of the work. Maybe not as simple as with an Arduino, but still pretty high level. This particular code uses the manufacturer's driver libraries, first to configure the pins for the motor driver output and for the button input, then to set up the timer for generating the motor signal, and finally a loop to turn the motor on or off based on the button input. If you've seen this kind of code before, it's all quite straightforward. If not, don't worry, we are about to improve it, because once again, what's really happening is hidden from us. Under the hood, it's really just memory operations, which we can again confirm by replacing every line with pure memory writes, the same memory writes syntax as before. First a few writes to configure the pins, then a few writes to configure the timer peripheral to generate the motor signal, and then a loop reading from a specific address to check the pin state. Yes, memory mapped I/O is not just about writes, it works the other way too, meaning we can also read from addresses to get input from the hardware. Finally, the writes to enable and disable the motor signal. Again, the addresses and values are found in the datasheet for the particular microcontroller. And technically, what we have here is strictly not just memory operations. We still got loops, if statements, all that logic to decide when things happen. But the actual control, the part that controls the hardware, does happen at the memory operations. Build, flash, and go. Yes, my trimmer turns on when I press the button. And here also with the new of the signal the microcontroller sends to the motor driver. So maybe memory mapped I/O is universal after all. Let's push it further. Another microcontroller board, this time one from Nordic, connected to a thermal receipt printer over serial. This Bluetooth board is obviously overkill for what we're doing here, but it's just for demonstration. And yeah, there is a library out there to control this printer, but by now you should be starting to realize that we don't need it. With memory mapped I/O, we can just write directly to memory instead. So cracking open another datasheet and finding the relevant addresses. First a few memory writes to configure the serial computation, only 3 writes needed for this. Then creating an array to hold all the individual bytes to send. First a few bytes to configure the font, then the first line of text, followed by a few new lines, second line of text, and more new lines. To be fair, the receipt printer is not just a mechanical box, it has a computer inside it too, which simplifies the code on our end. But if we crack it open, I would bet it's just another microcontroller doing memory mapped I/O like the rest of them. After the array, a loop then goes through all the characters and sends them out one at a time, waiting for each to go out. That's all it takes. Perhaps something to think about the next time we say no to that receipt. Build, flash, and so now we've seen memory map I/O in action on 3 different devices. Same mechanism everywhere. Even people building computers in Minecraft end up using memory map I/O. The core idea is simple, focused memory, and the hardware reacts. But before I use it to control this laptop as well, we should take a closer look at how it works. How can writing a value to a specific address in memory cause something to happen in the real world? To answer that, let's first recap what happens inside a microcontroller when we write to regular memory. Take the Arduino again. If you write a value to RAM, like setting a global variable, it just stays there. Put something in, get the same thing out. We compile this code into machine instructions that the computer can understand. Two in this case. One to first store the value into a register, and then another to write it into RAM. And we upload them to flash memory. Then inside the microcontroller is what roughly happens when those instructions run is that first there is a register keeping track of the current instruction, the program counter register. It points to the first instruction, and for the CPU to understand what it's supposed to do, it loads this instruction into the instruction register. Then the control unit, the one that directs the flow of the CPU, decodes this as a load instruction and executes it by toggling the control signals to load the value to one of its general purpose registers to temporarily hold on to the value. After that, we move on to the next instruction. The program counter implements. Same steps again. The instruction is fetched and decoded, but this time it's a store instruction, so the control unit instead activates control signals to put the address on the address bus and the data on the data bus. It also sets an extra control signal to tell the RAM it's time to respond. The RAM reacts by decoding the address further and storing the value into the memory cell at that address, where we can later retrieve it by reading from the same address. Okay, that's what roughly happens when we write to regular memory like RAM. So how does that compare to when we write to memory mapped I/O? Well, actually, it's almost the same. We can compare it to the line of code from earlier, the one that toggles the LED on the Arduino. It looks similar, except for the volatile keyword. This means it compiles into nearly identical machine instructions, just a different address value, which further means we should expect this code to follow a similar flow inside the CPU, right? And yes, the first instruction is executed the same way. But during the second instruction, there is a twist. This time, when the address hits the bus, the RAM block won't respond, because apart from the write enable signal, there is an address decoder block with its own set of enable signals. And this decoder block works kind of like a big hard-coded if-else statement, where each condition corresponds to an address range and each body an enable signal. This is where the designers of the chip decided instead of mapping all memory addresses to regular memory like RAM, they map some of them to other things like I/O, and this is why it's called memory mapped I/O to begin with. So this decoder block takes the address as input and then asserts the corresponding enable signal. In this example, it's going to enable the GPI hardware, and once enabled, the GPI hardware decodes the address further and writes the data value into one of its registers, which is then in turn wired to some additional control circuitry that further wires to an I/O cell, and that is what finally controls the physical pin that drives the LED.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone. But getting it.
Just maybe a bit more having big bells, and even the uncutting corners, my explanation. The actual implementation varies between chips, and physically, underneath it all, it's millions of logic gates firing coordination. But at a high level, this is more or less how memory mapped I/O works. And I think it's a clever mechanism because despite the underlying complexity, we can treat I/O just like regular memory. No special handling or instructions. The CPU doesn't need to know the difference, and neither does our code. This lets us write portable code that talks with I/O just like it talks with regular memory. One unified model for everything, which partly explains why we're stuck with C, why pointers are everywhere, and even why volatile string. You could kind of call it fundamental theorem of embedded system, because it's like the fundamental theorem of calculus connects differentiation and integration. Memory mapped I/O connects software and hardware. Maybe a bit of a stretch, but I like it. And as an embedded engineer, I find a certain calm in that no matter how complex things get, in the end, controlling hardware is just basic things in memory. But wait a minute, what about all those other mechanisms? software hardware? What about interrupts? What about DMA? What about port mapped I/O? What about channel I/O used in those mission critical IBM C mainframes? Yeah, fine. Memory isn't the only way code talks with hardware, but I dare to say it's by far the most common way, and it's still often used together with those other methods. You might still be skeptical though, and that's fair. So far, we're only seeing memory map I/O on these big computers, but what about real computers, like your phone or laptop? Yes, even their code uses memory map I/O solved with hardware. It's time for one last push to drive the point home. To change the screen brightness on this laptop, I can drag a slider in a fancy red curtain space. And yeah, that works fine. But if the idea of memory map I/O is truly universal, instead of using this slider, I should be able to just write memory, right? Now, on a system like this, running a typical Linux distribution, I can't just write the memory directly. For some reason, the OS developers don't want me to have that kind of power. To make it work, I have to recompile the Linux kernel and disable the restriction on direct memory access. Linux exposes physical memory to a special file called map located on the slash dev. Write to it, and you basically write straight to physical memory. You can do it in C, but there is a handy tool called devmap that makes it easier. Finding the right memory address, though, that's the hard part. There's no single data sheet for a laptop, and getting anything to happen can require a bunch of memory writes. So it takes some digging and guesswork, and even then, the OS might fight back. I'm not saying this is practical, I'm just showing it's possible. But screen brightness, that's one of the easier things to control. I finally found the address, and when I write a smaller value to this address, the screen gets darker, and when I write a larger value to it, it gets brighter. That's when finally so this was never about something else. Remember, memory map I/O is everywhere. Hardware isn't complicated, it's just memory. Once you realize that, you may start to believe that you can control anything. And even begin to question the need for all of that. So
Baik, mungkin sekian dari saya. Saya akhiri dengan wassalamualaikum warahmatullahi wabarakatuh.